Welcome back everybody to this first video on an extension of the concept of limit. We're going to call this continuity, and we're going to do the covering of this material in two parts. So today is part one. So the concept of continuity is actually fairly intuitive. We say that a function is continuous. We say that f of x is continuous, and I'm going to say here intuitively. It's not a formal definition. So f of x is continuous intuitively if we can sketch its graph. We can sketch its graph without lifting the marker from the whiteboard. That is for you, without lifting the pencil from, well, we're just going to say paper, but we could mean tablet, we could mean like anything that you can actually write on. So that's basically the idea. If I have to sketch the graph of something like this, then basically right here at this point, I have to lift my marker from my whiteboard right there at that point in order, when I go from left to right, in order to, when I get here, I need to continue over there. So I can't do this. That's not a function anymore, right? So basically, I have to lift the marker from the whiteboard, go there, and continue the graph. That means I have lifted the pencil to continue sketching the graph. That's a special graph. That is a graph that is not continuous. Right? That is a graph that is not continuous because of this actually jump. Right? We can actually call this a jump in the function. Yeah. On the other hand, if I have something like this, then basically in order for me to sketch this graph at, say, this point, if we just have to focus on one specific point, at this very point, did I have to actually leave the graph to go to another portion of the graph? No. So pencil not lifted. Pen or pencil not lifted. So it's an easy concept to grasp from an intuitive point of view. So a graph like this, which is smooth, which there is no jump, is a continuous graph. Once again, this is not a very formal definition. A formal definition will follow, but it gives you an idea of how this actually works out. And what we're going to do in this video is actually explore how discontinuous graphs relate to the existence of a limit at a certain point. So let us actually see if we can give a definition of continuity. So I will erase this in 2, 1, 0. And here comes a definition of a function being continuous at a point. So definition. F of x is continuous at a point x is equal to a. So I'm defining continuity at a point. If all, that's going to be important, if all of the following three conditions are satisfied. If all of the following three conditions are satisfied. Okay. Now, what are these conditions? The first one, the first condition. F of A, so the function, evaluated at the very point A we are investigating, f of A, must exist. What does that mean? It can't be, does not exist. It can't be D and E. Must exist actually means that it is equal to, well, not equal to, but element, let me just do this better, element of the real number system. So element of the real number system. So just this fancy symbol to say it's an element, it belongs to the set of real numbers. So as long as f of A is a real number, we're in business. The first condition is satisfied. The second condition has to do with the concept we studied in the previous chapter. The limit as x approaches A of f of x, this limit, again, must exist. Now you remember what that means, right? That the limit must exist. What does that mean? If you answered that the left limit is equal to the right limit, then you are correct. It means that limit as x approaches A from the right is equal to the limit as x approaches A from the left, and they both exist. And they both actually exist. So no crazy stuff here, no D and E, no infinity, nothing. Those two limits are the same and they both exist. Finalement, the third condition is actually quite simple. The outcome of A, which is outcome of 1, is f of A, and the outcome of 2, which is the limit, those two guys must be the same. If f of A is equal to the limit as x approaches A of f of x, and if all of these three conditions are satisfied, then we actually have that the function is continuous at the point x is equal to A. Good, so it's a fancy definition that actually comes into three parts. Let us see if we can show some examples of how this works. So I will erase this now in order to show some examples. Okay. All right, so the first example we have, example 1. Example 1, this is not very dark, so I'll use something a little darker. So consider the graph of f of x below. Okay, we'll sketch a graph in one little moment. Determine if f of x is continuous. Determine if f of x is continuous at, say, x is equal to A. So I'm just going to emphasize the fact that this is continuity at a point. Let us show the graph here. So y-axis, x-axis. Sorry if the lines are a little bit crooked. Okay, so I don't know, something like this. And we have here point A right here. And of course, in blue is the function f of x. Okay, good. So I just want to emphasize here that at the point A on the curve, there's an open dot. It's pretty clear from the graph, but I just want to make sure that everybody understands what I'm trying to draw. Okay, so is this function continuous at A? Intuitively, if I am going to sketch this, I'm going to hit some sort of a barrier here, this invisible thing that is an open point. I should be jumping over that if I want to continue sketching the graph to the right, yeah? So intuitively, that should not be continuous. Let us see under the conditions that we have if it is. Condition 1. What is the first condition for continuity? F of A must exist. So f of A, does it exist? Does f of A exist? Well, what is f of A? If it exists, we should be able to find it. And precisely when x is A, I don't have a y value. It's an open dot. F of A does not exist. Condition 1 is already violated. So condition 1 fails. Condition 1 fails. Now remember, for f of x to be continuous at A, I need all of my 3 conditions to hold. If one of them doesn't hold, do I need to check the other 2? No, I can stop right here. I don't need to check conditions 2 and 3 because condition 1 is not working out. So basically I can conclude right here that f of x is not continuous. Now there's a fancy word for not continuous, you might have heard it before. Discontinuous at x is equal to A. And voila, it's as simple as that. So our intuition that I had to actually lift my marker from the whiteboard to continue sketching the graph of f of x at the point A, making the graph discontinuous, that intuition is verified by the definition, by condition 1 of the definition. Good. We'll try another example. So let's get rid of this. All right. So example 2. Same question. So determine if f of x is continuous at the point A. Not going to rewrite the whole thing. Same question for f of x whose graph is below. All right, new graph for f of x. Change colors, change markers. Actually, let me push this a little to the left so I can do the work on the right side. That would make the whiteboard more efficient. Here's x, here's y. All right, so what kind of a graph would I like to have here? Something like this. That looks pretty much like the one before, yeah? Well, let me make it a little bit different by having a closed dot right above x is equal to A. So A is here, just like in the previous example. And this time, why don't we give ourselves a couple of y values here so we can analyze this a little more precisely. Let us call this, I don't know, let us call this 3. And let's call this other y value 5. Just for like putting in some numbers. Okay. So let us check our conditions. But before we do that, do you think actually that this is a graph of a continuous function? Probably not, right? because when I actually try to sketch the graph of this, right there I got to lift my marker, go up, fill that point, come back, and finish the graph. This is lifting the marker from the whiteboard, so it's very unlikely to be continuous, but we need to analytically find why. So how do we do that? We do this by verifying our three conditions. What are these conditions? Condition 1, f of a must exist. What is f of a? What is f of a? What do you think? From the graph, what is f of a? What's the value of the function precisely when x is a? Is it here? No, that's an open dot. It's right there. It's 5. F of a is actually equal to 5. And it exists. 5 is a number. It's not D and E. It's not some crazy thing. So condition 1, check. Condition 1 is satisfied. Condition 2, I need to verify that the limit as x approaches a of f of x. I need to verify that this limit exists. What is that equal to? Well, I think we have to investigate that a little bit, but we'll remember our very first lesson on limits, which were graphical limits. So I'm approaching a. Let me be here. Let me be here on the left of a and getting closer to a. Where is the function if I am here? This is the function. Let me get closer. Where is the function if I am here? And so on and so forth. As I get closer and closer to a from the left side, the function gets closer and closer to what y value? 3. Do I care if this is an open dot or a closed dot? Not in the least. It's not about f of a. It's not about getting at a. It's about I am getting close to what y value? Well, I'm getting close to the y value of 3 when I am approaching this guy from the left. So I'm going to put a little minus here. Good. Let me approach the same graph of the same f of x, but this time from the right side. So a from the right side. Let's investigate that as well. It's kind of a little bit of review of graphical limits, huh? Let me be on the right side of my target. My target, of course, is a. I am here, relatively close to a, on the right side of a. Where's the graph? Right here. Let me get a little closer. I am here. Where's the graph? These values, as I move closer and closer to a from right to left, these y values are getting closer and closer to what y value from the graph? To 3. Once again, open or close, je don't care, because I don't want to find what f of a is. I want to know what's the limit, which means what is the y value that I am getting close to. And I am getting close to 3. Haha! The left and the right are the same value. So I can conclude at the end of step 2 that limit with no direction, limit as x approaches a, no direction of f of x is equal to 3. And that is a number, and it exists, so I'm going to put a check mark because it means that condition 2 is satisfied. We're doing very well so far, right? And that seems to be contradicting our intuitive notion that we had earlier that, there's a jump in this graph. It should not be continuous. Well, condition 1 is pretty good. Condition 2 is pretty good. What about condition 3? Yeah. Many of you have already noticed that condition 3 is where things are going to fall apart. What is condition 3? Who remembers condition 3? You. Please tell me, what is condition 3? I don't know. I don't know your name, but I'll learn it eventually. What is condition 3? You're absolutely right. You're absolutely right. It's the outcome of condition 1 equal to condition 2. It's like limit as x approaches a of f of x. That has to be the same as f of a. You've noticed, huh? It's like the outcome of condition 1, which is f of a, equals to the outcome of condition 2, which is the limit. Now, is this happening here? Of course not. The limit answer is 3. The function answer is 5. That's a 3 right here. I'm going to make it look better. And they're not equal. So condition 3 fails. So big X, condition 3 fails. So conclusion. Since condition 3 fails, then we conclude what? Well, in order for me to have a continuous function at a point, I basically need all of my 3 conditions to be satisfied. It's not the case. So we conclude that f of x is not continuous or discontinuous at where? At x equals to a from this graph. That's the graphical notion that we need to master at the end of this first video on continuity. Good. We have time for another example. So I'll erase this and let's see if we can come up with another example here. Oh, these markers are actually marking the whiteboard quite in depth. Okay. So, same question, example 3, same question with the following graph. Example 3, same question for the function f of x, whose graph is given below, whose graph is given below. What do we have here? Well, a set of axes, first of all. And an x and a y. Now, what do we have? Let's have, I don't know, this. And then what about, I don't know, this. So this is the graph of f of x. Let's give ourselves a couple of pointers as usual. Oh, this is my standard 8 and some points on the y-axis. Let's put this as 4. Let's put this as 7 just to have some numbers. It's pretty obvious, huh? There is no way in the universe that I can actually sketch this graph without jumping from y equals 4 to y equals 7 at the point A, so this has got to be discontinuous. So really the only question that remains is which condition will fail us. So verifying condition 1, f of a, what do you say? F of a, does it exist? And if so, what is it? F of a. From the graph, at x is equal to a, what's the value of the function? Is it here or is it there? Of course it's there because that's where the full point is. F of a is 7. That number exists. Condition 1 checks out. Condition 2, let's investigate the limit as x approaches a of f of x. And that requires looking at the left and looking at the right. So looking at the left and then looking at the right, what will I obtain when I do the analysis of these two limits from the graph? What will I obtain? All right, approaching from the left. Approaching from the left. Let's approach from the left here. Nope, not with this. I am here on the left of A, relatively close. Where is the graph? Finding the graph. About at that height, that may be, I don't know, 3.2 something. Getting closer. Where's the graph? Oh, that y value is about here, maybe 3.5, 3.6. Getting closer. Where is that y value? Getting closer and closer. It won't get there. It's an open hole. We don't care. We want to know, what are you getting close to? we're going to be getting close to the value of 4. Let us approach this now from the right side. I am now here on the right side of A. Where is the graph? Well, I got to catch the graph here. What's the y value? Well, maybe, I don't know, 6 point something. Let me get closer. Where's the graph? Oh, pretty close to 7. I think we get the idea. As I'm getting closer and closer and closer to A from the right side, the y value being approached is 7. Once again, it has nothing to do with the fact that the point is closed or open. It is what we are getting close to that matters. We are getting close to 7. These two values are not equal to each other. Right away, I can tell that the limit as x approaches plane A of f of x does not exist. And that means that condition numéro 2, condition 2, fails. Condition 2 fails. Do I need to check condition 3? No, I do not. I can actually stop here and say that conclusion, those 3 dots means conclusion. You probably know that. And if you did not, now you do. Conclusion, f of x is not continuous at x is equal to a. I'm going to use here not continuous instead of discontinuous. They're equivalent. Is not continuous at x equals to a. Okay, well, that kind of gives you an overview, kind of a very simple introduction, I guess, to the topic. We will get into the more analytical part, the more algebraic part in the second video on continuity. So that's it for now. You stay well. I'll see you soon. Bye.